All right, looks like pretty much everybody is here. So today I have a few things planned for you. It's not going to be a heavy day with a lot of new stuff. There's one section we're going to cover, but it's a very simple section. So I want to start by practicing a little bit of homework problems. Let me get you guys set up here. There we go. So this, of course, is this is Calc 2, Section 2, and today is the 28th. We're going to talk about some homework problems. And then we're going to cover section 6.5, which is on average value. Which is a concept from statistics. So let me, I'm going to go ahead and close my door here. My wife is doing an interview downstairs. And we can get started. For the homework problems, I'm happy to do whatever you guys would like to do. So anything from the current homework set that you found a little bit intimidating or you haven't gotten done, or maybe you got it done, but you're not totally happy with how it went, anything like that. You guys tell me. You can type in chat. What problem numbers from this week's homework would you like to look at today? 11, 12, yeah. Yeah, we can start with 11 and 12. Those are both good problems. And if there are other problems that you guys would like to see, please go ahead and type those in the chat now. That way I'll have them all in one place. We can come back and take a look. So this is homework 1, problem 11. Here we want to integrate, and it's an indefinite integral, the function x to the 5 over 1 plus x to the 12. What I see when I see an integral like that, my first thought is that this factor in the denominator, the 1 plus x to the 12, since that's an even power, this kind of reminds me of 1 over 1 plus x squared. It makes me think of that arctan integral. That's where my brain goes when I see a factor in the denominator that's 1 plus an even power of x. Since we're learning about substitution, since this is coming from section 5.5, you can infer that we're probably going to solve this problem by making a substitution. And we have to figure out how this guy up here is going to play in. So if there's one thing that I would do to make a little bit more obvious what we're going to substitute for, it would be to rewrite the x to the 12 downstairs as x to the 6 squared. And this is coming from that rule for exponents. A to the b all to the c is the same as a to the b times c. And there's that algebra rule. So x to the 12, that's x to the 6 times 2. So that's the same as x to the 6 all to the 2. And now hopefully you can sort of see what we're going to sub for. X to the 6 has derivative 6x to the 5. So if I sub u or z equals x to the 6, I'm going to use the letter z because I do want us to start getting into the habit of using a letter other than u. I'm going to let z be x to the 6. Then dz, that'll be 6 times x to the 5 dx. And this 6x to the 5 dx, what I see is that I do have an x to the 5 dx in my integral. So I'll divide both sides by 6. I see that 1/6 dz is equal to x to the 5 dx. So that's my substitution. And if you want to, you could rewrite your integral like this: 1/1 plus x to the 6 squared times x to the 5 dx. And that will help you see exactly what's going to happen. This piece will become 1/1 plus z squared. And this piece, x to the 5 dx, that's going to be 1/6 dz. So this integral is equal to the integral of 1/1 plus z squared times 1/6 dz. Does everybody see the algebra steps here to here and here to here? Those are the two big things. Being able to see how to do the algebra, just how to mash the things together. Any questions on the mechanics of the substitution? Okay, so then we can pop out the 1/6. We're left with the integral of 1/1 plus z squared. What is that? What is the integral of 1/1 plus z squared? Why is this so nice? Does anything you know have a derivative that looks like this? Yeah, good, arctan. Rita got it. The inverse tangent function has a derivative that looks like this. So this is 1/6 times the inverse tangent. And you can write that using the inverse notation like I am here. Or you can write out ARCTAN. Inverse tangent of z plus c. And then because it's an indefinite integral, there aren't any bounds. We don't have to evaluate this between two numbers. Instead, we just tack on that plus c. But if I asked you this question and you gave me this answer and I couldn't see all the work in between, I would be very confused because what the hell is z? I asked you a question about apples and you give me an answer about oranges. So you just have to remember in these indefinite integrals and the integrals without bounds, you have to go back to your original variable. On the integrals that do have bounds, you don't need to go back to the original variable. You just evaluate between whatever your new bounds are when you change them. But here, this would be our final answer.
Professor, I have a question.
Yeah.
Is there any way to check our work in these kind of problems?
There absolutely is. I'm glad you asked. That was the next thing I was going to say. So you can check, you can always check an indefinite integral by differentiating. Remember what you're doing here is you're trying to find an antiderivative for this. So I claim that this is an antiderivative for this. How would you check that? Oh, well, you just differentiate this and see if you get that. So the derivative here, if I take d dx of 1/6 inverse tangent of x to the 6 plus c, first the c differentiates to 0. So it's really just the 1/6 arctan x to the 6 that I have to deal with. The 1/6 will come along for the ride. And then we just have d dx of arctan x to the 6. You have to remember that the derivative of the inverse tangent function is 1 over 1 plus whatever is inside there squared. So this will be x to the 6 squared. And then by the chain rule, you have to multiply by the derivative of x to the 6, the derivative of the inside function, which is 6x to the 5. And now what you'll see, if we put all this into one fraction, this is 6x to the 5 over 6 times 1 plus x to the 6 squared is x to the 12. You can cancel the 6's, and we do get x to the 5 over 1 plus x to the 12. So this is good. And yeah, you can always check your integration work by taking a derivative. While we're here, I want to make a quick note because I know this inverse trig stuff is stuff that not always covered very well. It's through no fault of their own. Many students don't remember this sort of thing. So let me show you a table. It's in your textbook. There's a much more complete version of this given in terms of integrals. If you go back to section 5.34 and you look here, there's a table of basic integrals. I expect you guys to know all of these, right? All of these, and you need to know them cold. These need to be things like, how do you spell the word sky? Like, it's got to be fast. This is stuff that, this is kind of where I draw the line at Calc 1. As you know, if you don't remember substitution from Calc 1, that's okay, we'll cover it. If you don't remember areas between curves or you didn't get to that in Calc 1, that's okay, we'll cover it. But these basic antiderivatives, these basic integrals, I do assume that you guys know these. I operate with that assumption. The ones that people tend to forget, I'll come back to my dot cam here, can be thought of in terms of derivatives. Okay, so the derivative of these inverse trig functions are things that people definitely from time to time need a reminder on. And we're going to be using them a lot in this class. So the derivative of arctan is 1 over 1 plus x squared. And so the integral of 1 over 1 plus x squared is arctan. You can think of it either way. Does anybody remember the derivative of the inverse sine function?
One over square root of 1 minus x squared.
Perfect. And then the derivative of the inverse cosine function is easy. Once you remember the derivative of the inverse sine function, you just slap a negative out front. The other one that we use from time to time is the secant function on here. I don't think it is. No, I'll go ahead and give it to you. We do use the inverse secant from time to time as well. This is 1 over x times the square root of x squared minus 1. Really, this should be an absolute value of x here. But when we use this, we use it in this form with the assumption that x is positive, so it's all okay. These are your inverse trig derivatives. And so the corresponding statement about integrals, the integral of each of these would be equal to these guys without the differential operator. Stuff that you want to know, especially these top two, we use these all the time. In fact, this guy, probably the most commonly used calculus statement in this class, besides derivatives of sine and cosine stuff. So make sure you commit these to memory. Make sure that you know all this stuff. All right, make sure you remember your basic antiderivatives from Calc 1. There were a few other problems from the homework that we wanted to look at, so let's go ahead and change back to that. Where'd my chat window go? 12 and 14, right? Okay. Yeah, 12 is fun. Here we want to integrate from 0 to 1, 8 times the cosine of pi t over 2. I'll write it like that at first. A word of advice: when you write your t's, I would give them this little tail so they don't look like pluses. Again, coming from section 5.5, we know the move is going to be a substitution. And the thing that makes this integral feel a little bit weird, this, cosine, that's not intimidating. 8, that's just a constant. It's the pi over 2, right? If I want to substitute for the inside, if this was just cos x, this would be easy. So again, I'll try to get in the habit of using a new variable, z equals, we'll go for the inside of cosine here, z equals pi t over 2. And so if we take the differential dz, remember this is the same as just pi over 2 times t. So this dz is just pi over 2 dt. There's no need for a quotient rule or anything like that there because pi over 2 is a constant. We will also need to change our bounds because this is a definite integral. And remember, in Calc 2, changing your bounds is not optional. You must do this. The way we find our new bounds is we take our old bounds and we plug them in to this equation. So when t is equal to 0, z is equal to pi times 0 over 2. That's 0 over 2. That's also 0. And when t is equal to 1, z is equal to pi times 1 over 2, or just pi over 2. When you get to Calc 3 and you're doing changes of variables there, this step is actually going to be the hard step. It's going to be challenging. You need to get into the habit of it now. Otherwise, you'll be writing down statements which are not true. And on exams, I will be taking points off if you don't do this, even if you go back at the end. So now if I go to implement this substitution, I can pop out the 8. I'll have integral from 0 to pi over 2. The cosine of pi t over 2 is just the cosine of z. But what to do with this dt? Well, if I come down here and I solve this for dt, I'll see that dz divided by pi over 2 is equal to dt. So I can plug this in for this. Like so. And now there's a bit of algebra. We do want to clean this up. Dividing by pi over 2 is the same as multiplying by 2 over pi. And 2 over pi is a constant, so it can come out. So I'll have 8 times 2 over pi integral 0 to pi over 2 cos of z dz. Any questions about how we get to here?
I have a question.
Yeah, please.
So when I was solving these problems, the first problems were very easy, but then when you got to like 12, then it was kind of like, what exactly goes through your mind when you have to pick what C is gonna be and what you're gonna substitute for, like what instead of using cosine of Z, like just like what exactly goes through your mind when you solve problems, like first step.
So I've got 2 different ways of thinking about this, and most problems I think about both ways. The first thing I do is I ask, what would I just like to get rid of? Like, what makes this thing feel shitty? Like, what about this problem do I not like? And then I try to substitute that away. So if this was just cos x, or just cos t, if it was just regular old cosine here, then I would know exactly what to do. I would take the antiderivative and evaluate between bounds. But it's not. So my goal with the substitution is to get rid of this and just replace it with a single simple variable. So here, that's enough to tell me that I should let z be the inside of the cosine function. Another way that it's useful to think about is to try and see your integrand as a composite function. Remember what composition means. It's one function that's been plugged into another. Kitty cat. Scratch me. So if I can visualize my integrand, the function I'm integrating, as a composite function, that is like an outer function and an inner function, then I will try to substitute for the inner function. That's kind of like what we did in this last problem. When I have to pick the substitution here, I'm thinking, what's my outer function and what's my inner function? Because I can rewrite this guy as x to the 6 squared, I start thinking of my outer function as 1 over 1 plus z squared, and my inner function as x to the 6. And that tells me, oh, well, what am I going to do with this? I should group that over with the dx to be a part of the differential for substituting. So I'm thinking of like this as my outer and this as my inner. And then once I've identified my inner, I try to make his derivative sit next to dx, or at least something close to his derivative sit next to dx, because I know I will need that when I make the substitution. So kind of two ways of thinking. First, try to picture your function as an outer and an inner. And also ask yourself, what about this problem sucks? Like, what do I not like about my integrand? What makes it hard for me to see an antiderivative? And in this case, it's just this stuff. If it was just plain old cosine, then I would say, okay, well, I want to, I would know how to antiderive cosine. So let me just try to turn this whole mess into a simple cosine. So I'll substitute for the inside. Now the answer, a thorough and perfect answer to your question is frankly a little bit complicated because there's an element of creativity here. You're making a choice. And so it's as much art as it is science, being able to spot a really good substitution. I remember I was taking this reading course in differential equations a long, long time ago. And there was an integral in that class that was incredibly challenging. I spent a few days on it and I was able to get it. And then there's this guy in the class named Eddie, who was very, very quiet. And at the end of class one day, he walked up to the professor and I was standing there and he said, well, this huge integral that, we've spent so much time on, you can do it with this little substitution. We were using very different techniques. We were using much more complicated, like series expansion techniques. And he found a way to do it with like this little substitution that utterly trivialized it. So it's spotting a good substitution is not always easy, but the two rules that I would encourage you to think about are, first, what do you not like in the problem? What would you like to get rid of? Try subbing for that. And then second, try to see your function as an outer and an inner, and ask yourself if, when you think of it that way, is the derivative of the inner function something that you can find sitting in your integrand? So those are the two little things. But yeah, it's not super obvious. I try to imagine how I would make the problem look nicer. What could I make go away? And then separate from that, ask, can I make that substitution? Do I have the necessary piece for the differential? So I'm sorry if that's not as satisfying as it could be, but those are the facts. And you'll, with more practice, you'll get much better at spotting these. It just takes a lot of time. That's the honest truth.
That was good. Thank you.
Okay. So from here, this is 16 over pi, and an antiderivative for cos z is not terribly hard to spot. Sine differentiates to cosine, so this will be sine of z. And I do not need to go back to my old variable t. I just evaluate this new function between his new bounds. So I just evaluate this from 0 to pi over 2. The 16 over pi comes along for the ride. And I get the sine of pi over 2 minus the sine of 0. Both of those are numbers that we know. The sine of pi over 2 is 1, and the sine of 0 is 0. So this is just 16 over pi. I think there was one other that was asked for here. 12, 14. Matthew wanted to see 14. Oh yeah, 14 is good.
Wait, Professor, can you go back for a second? I wasn't done copying. It'll
Oh,
take
sure.
like 10
Yeah, sure.
Thank you.
So while you're writing, we'll think a little bit about 14. It's a definite integral, so I know I'll have to change bounds when I substitute. Upstairs here, I've got this e to the 1 over x cubed, and then downstairs here, I have an x to the 4. So we should be thinking about what we'd like to get rid of here.
Okay, I'm done. Thank you.
Sure. What I see is when I go to integrate e to some stuff, I like that stuff to just be x, or to just be my variable. So when I see the integral in problem 14, my first thought is to try substituting for the exponent of e. So it's the integral from 1 to 2, e to the 1 over x cubed, all divided by x to the 4 dx. So if this was just e to the z, that would be nice. I'm not sure how this is going to play, but if this was just e to the z, that would make me pretty happy. That's certainly easier for me to integrate than e to the 1 over x cubed. So my first thought when I look at this is that I'd like to get rid of this piece. I'd like this to just be a single chunk, just a simple z. So I can try substituting for that. But I should be asking myself whether I have the necessary pieces. I need the derivative of this to be floating around. The only other thing I have is this x to the 4 downstairs. So maybe I'll try rewriting this as the integral from 1 to 2 e to the 1 over x cubed times dividing this by x to the 4. That's the same as multiplying by 1 over x to the 4. And now if we start thinking about the derivative of 1 over x cubed, we'll realize that we're actually in pretty good shape. This 1 over x to the 4 isn't exactly the derivative of 1 over x cubed, but it's pretty close. So let's see what happens. If we let z be 1 over x cubed, which is the same as x to the negative 3, then dz will be the derivative of this. That's negative 3 times x to the negative 4 dx. In other words, dz is negative 3 times 1 over x to the 4 dx. So this 1 over x to the 4 dx matches up with this 1 over x to the 4 dx. That's good. That means I just need to divide both sides by negative 3. So negative 1/3 dz, that is 1 over x to the 4 dx. So here's the stuff I need to make the algebra of the substitution go. The other thing I must do is change my bounds. So we'll do that here. When x is equal to 1, z would be equal to, let's see, 1 over 1 cubed. That's still 1. And when x is equal to 2, z would be equal to 1 over 2 cubed. Well, 2 cubed is 8, so it's 1/8. So here's all the stuff from my substitution. And when we plug it in, my integral goes from 1 to 1/8. E to the 1 over x cubed, that's e to the z, times 1 over x to the 4 dx, 1 over x to the 4 dx, that's negative 1/3 dz. So this will be times.
Wouldn't 1/8 be on the bottom portion of the integral?
So the
Or
reason why I like to arrange these the way I do in the box here, I always put the lower bound on the bottom. Old lower bound leads to new lower bound, and old upper bound leads to new upper bound. You're right that it's strange that the 1/8 is smaller than 1, but we have to preserve the structure that was given to us. So the 1/8 came from the 2. The 2 was the upper bound, so the 1/8 has to be the upper bound here.
okay,
But there is something we can do. There's a
you can flip it, right?
Yeah, exactly. So let me do a little constant juggling. I'll pull the negative 1/3 out, and then we'll have integral 1 to 1/8 e to the z dz. That's good. And then this kind of unsatisfying thing where the larger number should be upstairs, we can fix that by using this negative. If I absorb this negative, these guys flip over. So that will be 1/3, positive 1/3, integral from 1/8 to 1, e to the z dz. And now we're in good shape. You don't need to do this thing where you flip the bounds like that, but it is appealing to do for precisely the reason that you mentioned, that having the larger number on top is nice. That's what we're used to. From here, the antiderivative step is pretty trivial. Who differentiates to e to the z? Oh, e to the z. So this will be 1/3 e to the z evaluated between these new bounds from 1/8 to 1. We do not go back to our old variable, right? Because it's a definite integral, an integral with bounds, and we changed the bounds. We can save ourselves a shitload of time. You just go ahead and evaluate this new function between these new values. When I plug in 1, I just get e to the 1. And then I need to subtract from that what I get when I plug in 1/8. That's e to the 1/8. And we're done. Of course, e to the 1 is just e. E to the 1/8 you could write as the 8th root of e if you really wanted to. So either of these would be just fine. I do want to get a little bit more practice with U substitution. I have a couple other problems in mind that I would like for us to look at. But before we go there, there is new material to cover today. There's this little bit on average value of a function. So I'll give just a second. Any questions or anybody who's still writing on this one? And then we're going to talk about section 6.5 for a little. No, Solomon, you do not have to swap them. So the step where I switch these guys and make the negative go away, that's an optional step. You could just proceed from here and you would have negative 1/3 out front and these guys would be flipped over. So it's not necessary, but it's a nice move. Yeah, just make sure that your new lower bound came from your old lower bound and that your new upper bound came from your old upper bound. That's the only place there I could imagine someone getting into trouble. So this is what's called an orientation reversing substitution. It's a neat thing. Any other questions on this guy? Okay. So then section 6.5, it's not a hard section, but there is a little bit of neat stuff going on here. So I want to find the average value of a continuous function. Averages are things that you guys are used to. I'm sure everybody's computed an average of some sort in the past. Oh, focus. Focus, God damn it. Sometimes this camera, I swear. There, no, yeah, okay. So averages, if you wanted to calculate the average of a finite number of numbers, say of the numbers y1, y2, y3, all the way out to, maybe there's n of them, so I have n numbers. We compute, in statistics, you usually use the bar up here to indicate the mean or the average of a set. Sorry, my cats are being terrorists. No, what are you doing? You don't need to be like that, you know, you can be more polite. So to compute the average of a bunch of things like this, usually the way you would do it is just by adding up all the things. So there's n of them. And then you divide by the number of things. You can write this in the sigma summation notation as the sum from I equals 1 to n of the yi's all divided by n. So we're going to use a little bit of this sigma notation today. But is it possible to find the average of all the numbers output by a function f of x as x runs from x equals a to x equals b. So the picture here here's your function. Maybe here is a, maybe here is b. So what I would like to do, you know, there's infinitely many x's in here. In the interval a to b, right? Any interval has infinitely many x's in it, or numbers in it, which means there's infinitely many y values up here. And what's worse is it turns out to be a big infinity, right? What I would like to do is write down every single y value that occurs up here, add all of those up, and then divide by the number of them. But there's way too many. There's infinitely many. And it's actually a big infinity. There are multiple sizes of infinity. The smallest one is called Aleph 0. This is an Aleph 1 infinity. It's a big infinity. So there's no way I could ever write something like this down for every single y value in here, because I would have to add infinitely many things together to even get started. And then I would have to divide the answer by infinity, whatever the hell that means. So the way we kind of try to get around this is by building a Riemann sum. So what we're going to do is we chop the interval AB into finitely many pieces. This is how we get around the infinity issue. We chop it up into finitely many, they're called subintervals. Of equal length. And we call that length delta x. If they're going to be equal length, then that has to be b minus a over n. Finitely many, how many n of them? So this is called a partition of the interval AB. We partition AB, and then we kind of take some samples. So I'm going to redraw this picture a little bit bigger. And here's A, and here's B. What I want to do is add up all these y values and then divide by the number of them, but I can't get at that right away because there's infinitely many of them. So instead I start just by chopping this up. I'll call this x0, and then I'll move delta x over and call that x1, and then I'll move delta x over and call that x2, and we'll keep going just like that. This guy, maybe I'll call him xi minus 1. So the next one would be xi. And we keep going all the way till we get to b, which we call xn. So now instead of working with all infinitely many of them, I'm just going to work with the y values that come from these x values. So up here, this y value, I'm not going to write the x coordinate because it's there. This is f of xi. This guy would be f of xi minus 1. This guy would be f of x2. This guy would be f of x1. And this guy over here would be f of a, or f of x0. And this last guy over here, of course, is f of xn. And there's lots of others. In between here, in these dot, dot, dots, I've got lots of others. I'm just not writing them. Now, instead of thinking about areas and rectangles, we just go ahead and try to approximate the average value. So the average of all the f of x's should be approximately, here maybe I'm not getting all of them because I only have finitely many, but the average of these particular guys, well, that's going to be, first add them all up, f of x0 plus f of x1 plus f of x2 all the way out to f of xn. And there's n of them, so I'll divide all of this by n. That I can rewrite in the sigma summation notation as the sum from I equals 0 to n f of xi times 1 over n. And this is starting to kind of look like a Riemann sum. In fact, this process looks pretty similar to the Riemann sum process, except in there you're drawing in like some rectangles. Here I'm just interested in the y values. I'm not worrying about any rectangles or areas because I'm just trying to add up all of those y values. If, however, I very sneakily multiply by b minus a over b minus a, I guess I shouldn't write the x here because that, looks like the variable x. But if I multiply by b minus a over b minus a, I can group the numerator with this 1 over n, And that will give me a delta x. That'll be b minus a over n. That's delta x. And this guy, he's just a constant. So he can come out of the sum as 1 over b minus a. And then what's left in there would be the sum from 0 to n, f of xi times delta x, because b minus a that is delta x, b minus a over n. And now this looks not kind of like a Riemann sum, but exactly like a Riemann sum. So while the average value of all the f of x's is approximately this, as I send n to infinity, I'll actually have infinitely many x's in here, which means I'll get all the infinitely many y values up here. That's actually what I want. So therefore, the actual average value for which we write, the notation is f av. This is the limit as n goes to infinity of 1 over b minus a times the sum I from 0 to n, f of xi times delta x. As n goes to infinity, that Riemann sum turns into an integral. So we get 1 over b minus a, that's this just coming along for the ride, times the integral from a to b of f of x dx. So this is what f av is. That is how you find the average of all the outputs for f of x. Cool stuff, right? Those of you who are going to be working with statistics in a meaningful way, this is going to be a really important concept. This is how you find, if you have a probability distribution, a continuous probability distribution, this is how you find the average outcome or the expected value of that random variable. Any place in stats where you would use a mean or talk about distributions or averages, when the thing that's being distributed or the thing that's being measured, trying to find the average of, usually in stat we call those random variables, you'll end up needing this result. Now there is another way of interpreting it. There's a geometric interpretation that I would like to show you. AVE, AV. Sorry, so Tavi asked, what are the letters underneath the F here? AVE for average. So I would like to show you the geometric interpretation. For the purposes of your homework, this boxed statement is really all you need. They ask you to compute some average values. Not terribly exciting. Oh, and I only have, yeah, the colors don't come across here so well. So the next part, the geometric interpretation, I'm going to show you in the textbook. Underneath lim here, this is the limit as n goes to infinity. So n was the number of sample points. All right, I started out by calculating the average of n values, n numbers, n y values from this graph. And then I send n to infinity so I can get all of the y values. So in this expression, if I take the limit as n goes to infinity, that's what we wanted, right? That's what we were talking about. We're saying, how do I do this when there's infinitely many y's? And the answer is, well, you just take a limit, right? So think of each of these as like y0, y1, y2, y3. If I send n to infinity here, this expression looks a lot like this expression. So it's still an average, but it would become the average of the infinitely many y values that exist along this graph between a and b. And that's precisely what I wanted, is the average of all the f of x's. it's approximately equal to this finite sum. It's exactly equal to what happens as you send n to infinity. Okay, so let me show you here, because it's a little bit hard to draw and I only have so many colors to work with and it doesn't come across very well on camera. The geometric interpretation. All right, so you see here, they're doing the same shit we're doing. You average finitely many x values and then they divide by b minus a and multiply by b minus a. And they get the result that we had. All right, so the limit here is equal to this integral. So the average value is 1 over b minus a times the integral from a to b of f of x. That's good. You can do some computations. That's not exciting. The cool shit is here. Look at this picture on the left. The average value is the unique constant function such that the area underneath that constant function, that rectangular area, is equal to the amount of area bounded by the curve. So here the shaded black area is equal to the shaded blue area. And that's what this statement about the mean value theorem for integrals is really saying. If f is continuous on AB, then there is some number c such that the value of f at c is equal to the integral of f divided by the length of the interval over which you're integrating. If you compare this to the original mean value theorem, the mean value theorem that you learned back in chapter 2, back in Calc 1, it's just the same thing as this written in terms of derivatives. So there you would say f of c is f of x is equal to f primed of c for some particular value, right? That the tangent line is equal to, there's a place where the tangent line is equal to the secant line. If you rephrase that using the fundamental theorem of calculus in terms of integrals, then this is what you get. And so it's just a neat connection to something that you've seen before. I'll remind you what the original mean value theorem said. MVT from Calc 1 says, if f is differentiable on AB and continuous on the closed interval AB, then for some number C in the open interval AB, f primed of C is equal to f of B minus f of A over B minus A. And if you multiply both sides by B minus A, you can rewrite that as f primed of C times B minus A equals f of B minus f of A. And this is the mean value theorem, saying that the average rate of change for the function over the interval AB is equal to the instantaneous rate of change somewhere in between. So if you have a secant line, somewhere in between there is a tangent line of the same slope. The picture for that looks like this. And here's A, and here's B. So your secant line there looks like this. And what this theorem does is it says, I promise you, there's some point where you have a parallel tangent line. So here would be C. Compare this to the mean value theorem for integrals. Which says that, yeah, that the integral from a to b of f of x dx, there is some c, so that this is equal to f of c times b minus a. So compare this to this. You see the difference, right? There's not much. Here you have an integral, here you have a derivative, but they're really saying the same thing because, you know, derivatives undo integrals. If you were to differentiate through this, you would get this. And here the geometric interpretation is that you can find a constant where the height of that constant is such that the area enclosed in this rectangle is the same as the area bounded by the curve. So it's neat stuff. But for the purposes of this class, we're really never going to come back and address this in any meaningful way. So I just wanted to show you now what we can. And it gives me an excuse to give you some more integration problems. So section 6.5 is going to be deeply important to those of you who are going into fields where statistics are relevant. And you might be surprised just how many fields there are like that. You know, if you're studying physics or chemistry or any sort of hard science these days, it's pretty much all down to analyzing lab data, and the methods that are used to analyze lab data are statistical. So this concept of an average value is an important one. And of course, if you divide both sides here by b minus a, the object that shows up on the left, this is f_av. Okay. So let's do a calculation or two. Let's grab some examples from your book, and I'll make sure they're nice and challenging. Okay, sweetness. Thank you. So let's find, let's see, I think this one I gave you in your homework, so I don't want to spoil it. Let's do number 4. Let's find the average value of 1 over, or t over the square root of 3 plus t squared from 1 to 3. What was it? T squared plus 3, 3 plus t squared. Okay, so here's my function. They're using the variable t instead of x, that doesn't matter. Here's my interval, so a is 1 and b is 3. So f_av is 1 over 3 minus 1, 1 over the length of the interval, times the integral from 1 to 3 of f of t, which is t over the square root of 3 plus t squared dt. So the front is just 1/2. I'm not worried about that constant, but how do I do that integral?
Can you do like use substitution maybe?
Yeah, we're going to need some sort of substitution. What would you like to substitute for? And this connects to what we were talking about before. How do you pick your substitutions? What is it about this integral that's hard? What would we like to make go away?
The root, probably.
Yeah, the stuff under the square root downstairs. If that was just the square root of t squared or the square root of, you know, t cubed or the square root of any straight power of t, that would be easy enough to handle. But because the square root doesn't play nice with addition, I can't like distribute the square root to this and this separately. There's no nice way for me to clean that up, so I'd like to get rid of it. So I want to substitute for 3 plus t squared. And looking towards that, I'm going to think, okay, well, what's my outer function and what's my inner function I can peel that t off the top and write it over here next to my dt, because the derivative of 3 plus t squared is 2t. So I know I'll need that t dt in my substitution. So the substitution looks like this. I'm going to let z be 3 plus t squared, which means dz is 2t dt. So 1/2 dz, that is t dt. I also need to change my bounds. When t is equal to 1, z will be 3 plus 1 squared, that's 4. And when t is equal to 3, z will be equal to 1 plus, I said 1 plus 3 squared, 3 plus 1 squared, okay, yeah. When t is equal to 3, I'll have 3 plus 3 squared. That's 3 plus 9, which is 12. What the hell is that? Right. So here's all the stuff I need for my substitution. This t dt, that's 1/2 dz. And this piece will be 1 over the square root of z. So I've got a 1/2 out front, that was already there. My new integral runs from 4 to 12. 1 over the square root of 3 plus t squared is 1 over the square root of z. And t dt is 1/2 dz. So this is how my integral looks at the start here. I can shuffle the 1/2 out front with the other 1/2 to make 1/4. And I can rewrite 1 over the square root of z as z to the negative 1/2. And then finally, to find an antiderivative, I need to increase this power by 1 and then divide by that new power. Negative 1/2 plus 1 is positive 1/2. So this is 1/4 times z to the positive 1/2 divided by positive 1/2, evaluated between 4 and 12. And I can continue that over here. Before I go plugging in, I should clean up algebraically a little bit. Dividing by 1/2 is the same as multiplying by 2, and I can bring that out front. So 2 times 1/4 will bring that back to 1/2. And then z to the 1/2, that's the same as the square root of z. And it'll be nicer to evaluate from there. If I plug in 12, we get the square root of 12, which is not super nice. When I plug in 4, I get the square root of 4, which is super nice. 12 is 4 times 3. So this is 2 square roots of 3. And then 4 is 2 times 2, so that's just minus 2. And then you could distribute the 1/2. And you get the square root of 3 minus 1. So if there was time, I would like to look a little bit more deeply at some things that can go wrong and weird with substitutions. Davis asks, so you're required to simplify your square roots? Yeah, I mean, so it depends on the problem. If you left this as the square root of 12 minus the square root of 4, I wouldn't take points off for it necessarily, but see how much nicer this is than this. It's worth the time, and you should be comfortable with it. There will be problems where that sort of algebra makes the difference between being able to finish the problem and not finish the problem. So certainly I expect you to be comfy with it. But on a problem like this, I wouldn't take off points if you didn't. So yeah, fair question. Any other questions about this one? They should be on the hook. If they're not there, then I'm not sure. But I'm almost done. Okay, so how are we doing on time? Yeah, I got a few more minutes of your time here. How did the 1/4 turn into a 1/2? So from here to here, I had this 1/4 times 2/1 times z to the 1/2 from 4 to 12. So this dividing by 1/2 is the same as multiplying by 2/1, and then the 2/1 and the 1/4 come together to turn that back into a 1/2. Other questions on this guy? Okay, so there's one or two other sort of integration problems I wanted to look at with you guys today, because I want to highlight the sort of things that can go wrong when you try to substitute. So far, all the examples we've seen, everything goes really well. But we've said, you know, oh, if everything doesn't cancel, or if you're not able to use this piece in the differential perfectly, it can cause problems. So I want to just take a look at something going wrong. So if I wanted to do the integral, this is one of my favorites, e to the x over 1 plus e to the 2x dx. This is a problem that's begging for a substitution, but it's possible to miss the substitution you should use. And it's definitely possible to try to grab the wrong thing. So one thing I've seen people do with this is try to substitute z equals, for the whole bottom, 1 plus e to the 2x. If you do that, then your derivative, your differential dz, the 1 differentiates to 0, e to the 2x differentiates to e to the 2x times 2. Because remember, e to some stuff, you prime that, you always get e to that stuff back, but then by the chain rule, you have to multiply by the derivative of the stuff. And here, if you then solve this for dx, you get dz over e to the 2x times 2 is equal to dx, and you can try to plug that in. The e to the x up here, you can hope will be gobbled up by the differential. We'll just write it down. So I've got e to the x over 1 plus e to the 2x, that's my z. And then if I plug in for dx, dz over e to the 2x times 2, the e to the x and the e to the 2x, they don't cancel perfectly. You can try to work with it. You can pop out the 1/2. You can group the e to the x with the other piece. And there is some cancellation that happens here. Remember, e to the 2x, that's the same as e to the x all squared. So you could write this as 1/2 integral 1 over z e to the x over e to the x all squared, and then cancel one of them. Sorry, this should be a dz. Then cancel one of them. But you're still going to have an x floating around in here. You'll have 1 over z times 1 over e to the x dz. And remember the cardinal rule for substitutions, you can't do anything until every single piece is in terms of the new variable. So here I got rid of my dx. I don't have any dx's anymore. It's dz's. This piece is nice. It's just 1 over z. That's fine. But this piece is a problem. He hasn't gone away. I still have some x stuff even after plugging everything in for my substitution. So this piece is a problem. You must get everything in terms of the new variable before doing any integration. So the question is, how do we handle this sort of situation?
Did you have subbed e to the x for u?
Yeah, we could have made a different substitution. And that's the first thing that should come to mind is that maybe I just chose the wrong substitution because there's an element of choice there. And yeah, if you come back to this and you sub z equals e to the x instead of subbing for the whole bottom, it'll work out beautifully. It's not a hard problem. It comes out to an arctan. So that should be the first thing that runs through your head. But what if you know for sure that that's the substitution you wanted to make? Either because someone told you to or because it's the only thing that makes any sense. So here, right, so try subbing for something else. All right, and I'll leave, for this problem, I'll leave that here, right? That's all. So you can go back and try a different substitution. This is what it looks like when shit doesn't work out. Yeah, not everything goes away. You're not able to get everything cleanly in terms of the new variable. Your first thought should be to try something else. So if you go back here, try just z equals e to the x. This is actually really similar to number 11 that we did at the start of class. So I'm not going to go through that. We have just a little bit of time. But I do want to show you how you can force things to go through. I could force this substitution through, the bad one. There is a way to make it go. And I'm going to show you what that looks like. But I'm going to do it with a different example just to give us more flavor. So here I want to force the substitution z equals ln x in the integral maybe we'll say from 1 to e sine of ln x dx. So this is actually not a bad substitution. But what you'll see when we get started is that, well, the inside here, this will be nice. This will just be sine z. The relationship between dz and dx, I don't have the 1 over x here that I would need to normally make this substitution. So I'll just start writing things down. If z is ln x, then dz is 1 over x dx. And I definitely don't have a 1 over x anywhere here I can work with. I'll change my bounds. When x is equal to 1, z is equal to the ln of 1, which is 0. And when x is equal to e, z is equal to the ln of e, which is 1. And if we go ahead and just try to write this down, this will now go from 0 to 1. I have sine z. I can solve for dx here. So if you multiply both sides of this by x, you get x dz is equal to dx. So this dx I can replace by x times dz. But of course, this is a problem. I still have some of my old variable floating around. I need to rewrite x in terms of z in order to proceed, in order to apply any of the integration techniques that we're aware of, I must rewrite this in terms of z. Do I have anything on the page that tells me how x and z are related to each other? I think if you go back to the first lecture video, yeah, we did something a little bit like this on one of the problems in the first day. So if you solve the substitution for the original variable, so say, but we know that z is the natural log of x. So then, yeah, if you exponentiate on both sides, you'll get e to the z equals e to the ln x. But e to the ln x is just x, so e to the z is x. So this guy is really the integral from 0 to 1 sine z times e to the z dz. And this is now looking good. Now everything is in terms of the new variable. Now you guys don't know how to do this integral yet, but you're going to learn. This is actually one of the integrals we'll learn how to do on the very first day when we talk about new integration methods. This requires what's called integration by parts, or a backwards product rule, right? If I wanted to differentiate this, sine z times e to the z, I would use a product rule. So if I'm going to integrate it, I need a backwards product rule, and that's called integration by parts. And I'll be teaching that to you guys, not next week, but I think the week after. Next week, we're going to be talking about volume problems, so some more geometry stuff. But the week after that, we'll start on chapter 7, and that's where you'll learn integration by parts. And in order to solve this problem, the original problem here, you would want to make this substitution, and then get to here, and then do integration by parts. So the problems can get quite long. They can get quite tricky. The IBP for this, the integration by parts for this, is not trivial. It's a little complicated. So this x came from the dx here, right? When I take my differential dz, I got 1 over x dx, because z is ln x. Derivative of ln x is 1 over x. So what I didn't have was a nice way to incorporate the 1 over x, because I did not have a 1 over x here. So what I did is I solved this for dx. Dx is equal to x times dz. And then I just plugged that in for dx. So dx is x times dz. This piece is dx. And then the problem is that I still had an x floating around. So I had to do something with that. And the only way to get rid of that was to go back to my substitution, solve it for x, and plug it in. You can always do this. You could do this on the problem that we looked at before also. So if you come back to this guy, if you wanted to force this substitution through, I'm not saying you should, I'm not saying it's a good idea, you can solve this for x and then plug that in for x here. And it's going to be a pretty nasty expression. But it would work. It would get you to the next step. So even when your substitutions don't go through, at least not right away, you can force them through this process. However, I did these 2 examples, not just this one, to point out that you shouldn't usually, right? Most of the time, if your substitution doesn't go through, you should try something else. It's usually a hint that you didn't choose the optimal substitution. However, if for some reason you know that that's the optimal substitution, or you just really, really want to try it, you can force it through like this. And that is the end of what I wanted to show you guys today. So I think this is probably where, and we're a little bit over, where we'll end the video. Are there any questions you guys wanted to ask before we part ways for the day?
Is there class on Monday?
Mm-hmm. Should there not be? Is there a holiday or something? Monday is August 31st. Yeah. I mean, as far as I know, there is class on Monday, unless there's some reason for there not to be.
Oh, I was thinking it's Labor Day, but that's next week. Sorry.
Yeah, I think September 9th is our first holiday. or maybe September 7th. But yeah, look in the syllabus. I do have all the holidays in the syllabus there. Alex, what would have been a better substitution for the previous problem is just e to the x. Yeah, the way you do integral e to the x over 1 plus e to the 2x dx is you let z be e to the x. So dz is e to the x dx. So this piece right here, this is your dz. And then you rewrite as 1 over 1 plus z squared dz, because e to the 2x is e to the x squared is z squared. And then from there, it's just straight arctan. This is the inverse tangent of z plus c. So that's arctan of e to the x plus c. Oh, this guy requires integration by parts. There is no nicer substitution for this one. All right, so I use this as an example of a forced substitution that you force through because this is the right move. There's really nothing else you can try substituting for here. So yeah, there's really no other move here besides this. And then once you force that through, you'll get here. And from here, you'll need a technique that we haven't learned yet called integration by parts, but I'll be teaching that to you when we get to chapter 7. Any other questions, guys? Okay, then remember you have homework due on Monday. I do have an office hour this afternoon from 3:30 to 4:30, so if you want to solve some more problems, feel free to come by then. Otherwise, I will see you all on Monday. All right, take care. Have a good afternoon.